Everyone, today I am going to read the chapter Non-Aqueous Solvents of Inorganic Chemistry from Pardeep's book by Dr. K.K. Bhasin. Chapter 8 Non-Aqueous Solvents. A solvent is generally defined as a liquid which has the ability to dissolve other substances. Water is considered to be a universal solvent since ancient times. Majority of the reactions are also carried out in water because of its easy availability and unique physical and chemical properties. There are solvents other than water that can be used to carry out chemical reactions. Solvents other than water are called non-aqueous solvents. Before we discuss the chemistry of non-aqueous solvents, it is appropriate to understand the important role of solvent plays in the chemical reaction. 8.1 Role of solvents in a chemical reaction. A solvent has two important roles in chemical reaction. The first and the most important role is to bring the reacting substances close to each other in a finely divided state. If the reactants are not intimately mixed, the rate of the reaction will be very slow. For example, the reaction between barium chloride and silver nitrate in the solid state will proceed very slow. BaCl2 solid plus 2AgNO3 solid is equal to 2AgCl solid plus BaNO3 twice solid. However, in aqueous solution, the reactions proceed very rapidly. Thus, the role of solvents is to accelerate the rate of the reaction. In addition, it is possible for a solvent to change the course of the reaction. In water, barium chloride and silver nitrate reacts with the twinkling of an eye to form white precipitate of silver chloride. The same reaction in liquid ammonia is completely reversed. 2AgCl plus BaNO3 twice liquid in presence of liquid ammonia converts into BaCl2 plus 2AgNO3. A solvent also affects the rate of the given reaction. For example, the reaction between iodoethane and triethylamine occurs to form tetraethyl ammonium iodide at a reasonable speed in hexene. In the above reaction is carried out in benzene. The rate of the reaction becomes 80 times that of hexene. In acetone, the rate of reaction is 500 times, whereas in nitrobenzene, the rate of reaction is 2800 times. We can say that the rate of above reaction in various solvents proceed in the order. Nitrobenzene is more than acetone, is more than benzene, is more than hexene. Another important role of the solvents is to allow rapid separation and purification of the products. The precipitation of the chlorides in the above reaction allows for an easy separation of the products. We should recall that silver chloride is insoluble in water, whereas barium chloride is insoluble in liquid ammonia. Suppose you are asked to prepare anhydrous sample of copper sulfate. How will you prepare it? Definitely, you cannot use water as a solvent. This means we need another solvent. Anhydrous copper sulfate can be cleanly and conveniently prepared in the molten solvent mercuric bromide. According as CuBr2 plus HgSO4 in presence of HgBr2 is equal to HgBr2 plus CuSO4. 8.2 Physical properties of solvents. The selection of the solvent in a reaction is generally made with regard to some specific properties that may help to carry out the reaction by effectively dispersing the reactants and separating the products more conveniently. Some of the important physical properties of the solvent are discussed below. First, melting and boiling point. Majority of the chemical reactions are carried out in the liquid phase. As a result, the liquid range, that is temperature range between melting and boiling point, determines the usefulness of a particular solvent. Melting and boiling point of several solvents are given below. An inspection of table 8.1 reveals that water has an excellent liquid range from 0 to 100 degrees Celsius. As a result, it is an ideal solvent for carrying out chemical reactions in solution at room temperature and atmospheric pressure. Both liquid ammonia and liquid sulfur dioxide are ideal solvents for carrying out the reactions at low temperature. Second, dielectric constant. Dielectric constant measures the polar nature of the solvent. This property is used to evaluate the solubility of polar or nonpolar compounds in a solvent. According to Coulomb's law, the force between two charged particles is given by the expression F is equal to E1 E2 divided by dr square, where E1 and E2 are the charges on the two particles, R is equal to internuclear distance between the particles, D is equal to dielectric constant of the solvent. A high value of dielectric constant indicates that the force of attraction F between the charged particles is less and hence a small amount of the energy is required to separate the ions. It means that it is easy to dissolve an ionic solute in a solvent of high dielectric constant. In other words, dielectric constant determines the ability of a solvent to dissolve ionic compounds. Thus, solvents with high electric constant should be able to dissolve ionic and polar compounds. A solvent is considered to have high dielectric constant if the value lies between 50 to 80, a medium dielectric constant if the value lies between 20 to 50, and a low dielectric if the value lies between 2 to 20. Thus, solvents like liquid ammonia and liquid sulfur dioxide with low dielectric constant should show decreased ability to dissolve ionic compounds, especially the multi-charged ions. As a result, carbonates, sulfates, and phosphates are less soluble in solvents with low dielectric constant. The dielectric constant and the polarity of solvents are related with each another. Table 8.2 lists the dipole moment and dielectric constant of some solvents. Third, heat of vaporization and fusion. Heat of fusion is defined as the amount of heat absorbed by 1 mole of the substance to change from solid to liquid state. Similarly, the amount of heat absorbed by 1 mole of the substance to change from liquid to gaseous state is known as molar heat of vaporization. The magnitude of heat of fusion and vaporization gives us some insight into the nature and strength of forces holding the molecules in a solid or in liquid state. A high heat of vaporization suggests that the intermolecular forces operating in the liquid state are strong and vice versa. Therefore, the heat of fusion and particularly the heat of vaporization are significant in evaluating the usefulness of the solvent. The ratio of the heat of vaporization to the boiling point on the absolute scale Kelvin is a constant called Troughton's constant, and it has a value around 21.5 for normal liquids. Normal liquids are characterized by single molecules without any bond between them. A value higher than 21.5 suggests association of molecules of a liquid to form larger aggregates. Such liquids are called abnormal liquids, which include ammonia, water, hydrogen fluoride, and sulfur dioxide. We have already learnt that molecules of liquid which undergo association and polarity are polar. Polarity in a molecule arises when the electron pair forming the bond is shared unequally between the two bonded atoms. Association between polar molecule arises from the tendency of polar molecules to orient themselves so that the positive end of the molecule are near the negative ends of the adjoining molecules. In addition, the polar molecules surrounds the positively charged cations in a way that the partially negative ends of the polar molecule are oriented towards the cation. Similarly, the polar molecules surround the negatively charged anions in a way that the partially positive end of the polar molecules are oriented towards the anion. Water, being a polar molecule, orients its negative end towards the cation, forming the first shell of water molecule around the cation. Figure 8.1 shows how the polar water molecule orients themselves around the cation. A careful inspection of the table 8.3 reveals that the heat of fusion of water and ammonia are nearly similar. It implies that the forces which hold the molecule together in water and ammonia are nearly of the same magnitude. The heat of fusion in case of sulfur dioxide is relatively high compared with that of hydrogen fluoride, suggesting that forces holding hydrogen fluoride molecules are weaker. Fourth, viscosity. It is an important property of solvents. Viscosity measures the difference in the rate of flow of liquids. Water, liquid ammonia, and lower alcohols flow rapidly under gravitational forces and have low viscosity, whereas high molecular weights, hydrocarbons, and hydrosulfuric acid are highly viscous and flow at much lower rate. Viscous liquid lower the mobility of ions and thus reduce the electrical conductance of solutions of the electrolytes. Experimental difficulties with viscous solvents are observed in precipitation, crystallization and filtration processes. 5. Self-ionization. The acidic and basic nature of the solute dissolves in a solvent depends primarily upon the self-ionization of the solvent. Any solute that by direct ionization or interaction with the solvent gives the cationic characteristic of the solvent resulting from self-ionization of the solvent is called an acid. Similarly, a base is any substance that gives the anionic characteristics of the solvent. Self-ionization of some solvents are given in the table below. 8.3 Types of solvents. Non-aqueous solvents can be broadly classified into 4 types, viz. Protonic and non-protonic solvents, acidic and basic solvents, ionizing and non-ionizing solvents, coordinating and non-coordinating solvents. The above classification is based primarily on the chemical properties of the solvents and are discussed below. Protonic and non-protonic solvents. Protonic or protic solvents are those from which the hydrogen ion H positive can be abstracted. Some of the commonly available protonic solvents are H2O, HF, HCN and H2SO4. Non-protonic or aprotic solvents are those from which hydrogen ion H positive cannot be abstracted easily. Frequently encountered examples of such solvents are CHCl3, C6H12, liquid SO2, etc. Acidic and basic solvents. Solvents which are capable of donating hydrogen ions H positive are called acidic solvents, whereas the solvents which are capable of accepting H positive ions are called basic solvents. Examples of acidic and basic solvents are acidic solvents HF, H2SO4, CH3, COH, etc. Basic solvents NH3, pyridine, hydrazine, etc. Ionizing and non-ionizing solvents. There are several solvents which undergo auto-ionization or self-ionization to different extents. Such solvents are known as ionizing solvents. Frequently encountered examples of ionizing solvents are given below. There are another class of solvents which are non-polar and do not ionize at all. Such solvents named as non-ionizing solvents. Examples are benzene, hexane, tetrachloromethane, etc. Coordinating or non-coordinating solvents. There are several solvents which are capable of coordinating with the ions of solute. Such solvents are designed as coordinating solvents. Commonly used coordinating solvents are ammonia, dimethyl sulfoxide, acetonitrile, nitromethane. On the other hand, solvents which are not capable of coordinating with the ions of solute are called non-coordinating solvents. For example, benzene, hexane and tetrachloromethane are non-coordinating solvents. 8.4 Liquid ammonia as a non-aqueous solvent. Liquid ammonia is one of the most thoroughly studied non-aqueous solvent due to its ability and water-like properties. These days, liquid ammonia is used very frequently as a solvent for many types of organic and inorganic synthesis. Ammonia is an associated solvent through hydrogen bonding, although the extent of hydrogen bonding is far less compared to that in water. As a result, the melting and boiling points of liquid ammonia are lower than those of water. Some of the important physical properties of ammonia are listed. The corresponding values of water are also listed in the table for the comparison. A careful inspection of the table 8.5 reveals that the dielectric constant of ammonia 22 is smaller than that of water. As a result, liquid ammonia is much better solvent for organic compounds than water. On the other hand, liquid ammonia is a poorer solvent for ionic compounds than is water. There are, however, a number of ionic compounds which have higher degree of solubility in liquid ammonia. Ammonium salts, regardless of the anion, are highly soluble in liquid ammonia. Inorganic compounds with highly polarizable anions, iodide, thiocyanates, are more soluble than the non-polarizable anions, fluoride, chloride. Solubility of halides decreases from iodides to chlorides. It is noted that the highly charged ions with high charge density like fluorides, hydroxides, oxides, sulfates, carbonates are insoluble in liquid ammonia. Autoionization of liquid ammonia. Liquid ammonia undergoes autoionization in a manner similar to water. However, the extent of autoionization is smaller than that of water. 2NH3 is in equilibrium with NH4 positive plus NH2 negative. The ionic product of ammonia at minus 50 degrees Celsius is 1.9 into 10 raised to power minus 33, which is very low compared to that of water. Chemical reactions in liquid ammonia. Chemical reactions occurring in liquid ammonia are similar to the reactions occurring in aqueous solution because liquid ammonia is similar to the water as a solvent. Some of the important reactions that take place in liquid ammonia are given below. First, acid-base reactions. The autoionization of ammonia gives NH4 positive and NH2 negative ions. 2NH3 is equal to NH4 positive plus NH2 negative. According to the solvent system concept of acids and bases, any substance that by direct ionization or by interaction with the solvent gives the cationic characteristic of the solvent, resulting from the autoionization of the solvent behaves as an acid in the solvent. Similarly, a base is a substance that gives the anionic characteristic of the solvent. Thus, NH4Cl would behave as an acid whereas KNH2 would behave as a base in liquid ammonia. Therefore, the neutralization reaction would be acid plus base is equal to salt plus solvent. NH4Cl plus KNH2 is equal to KCl plus 2NH3. Acids and bases in liquid ammonia are called amino acids and amino bases respectively. Thus, amino acids are substances which in liquid ammonia furnishes NH4 positive ions, whereas amino bases are the substances which in liquid ammonia furnishes NH2 negative ions. Solutions of metal in liquid ammonia. A unique feature of liquid ammonia as a solvent is its power to dissolve the alkali metals and to a lesser extent the alkaline earth metals and aluminium. The metals dissolve to impart blue color. The blue colored solution is independent of the metal dissolved and has a broad maxima around 15,000 angstrom. The solutions are extremely good conductors of electricity. As the concentration of the metal is increased, the solution becomes bronze colored up to the limit Li 16m, Na 10m, K 12m. The dilute solutions are paramagnetic while the paramagnetic behavior decreases with the increase in concentration of the metal. Highly concentrated solutions have conductivities nearly as high as pure metals. The equivalent conductivities of lithium, sodium and potassium are given below. It is believed that the blue color of the solution is due to the presence of alkali metal ions and free electrons in liquid ammonia. Metal is in equilibrium with metal positive plus electron. In dilute solution, the metal ion and the electrons are ammoniated as, or simply, metal in presence of NH3 is equal to metal positive ammonium plus electron negative ammonium, where Am stands for ammoniated species. Solutions of alkali metal in liquid ammonia are metastable. A small amount of impurity is sufficient to catalyze the formation of amide. A rust nail will be capable of serving as a catalyst for the formation of sodium amide. 2Na plus 2NH3 in presence of Fe2O3 is equal to 2NaNH3 plus H2. However, if both alkali metals and ammonia are extra pure, the alkali metals dissolved in liquid ammonia can be kept for many weeks at low temperature and one can recover the alkali metal on evaporation of the solvent. However, when alkaline earth metals dissolved in liquid ammonia are evaporated, the free metals are not obtained. Instead, ammoniates of the type MNH36 are obtained where M is the alkaline earth metal. Reactions with amino acids. Amino acids is a substance which in liquid ammonia supplies NH4 positive ion. Thus all ammonium acids salts irrespective of the anion are amino acids in liquid ammonia. These acids undergo a number of acid-base reactions given below. First, the amino acids react with the reactive metals alkali, alkaline or other metals and liberate hydrogen gas. Na plus NH4Cl in presence of liquid ammonia is equal to NaCl plus NH2 plus hydrogen. Second, ammonium salts dissolved in liquid ammonia are used for the synthesis of various hydride. For example, reaction of magnesium silicide and magnesium germanide and ammonium solution of ammonium bromide give high yields of silanes and germanes respectively. Mg2Si plus 4NH4Br in presence of liquid ammonia is equal to 2 MgBr2 plus SiH4 plus 4NH3. Mg2Ge plus 4NH4Br in presence of liquid ammonia is equal to 2 Mgbr2 plus GeH4 plus 4NH3. Third, amino acids undergo proteolysis in liquid ammonia. A number of compounds like urea, acetamide, sulfamide, sulfamic acid, and that do not donate proton to water readily donate protons to NH3 in liquid ammonia. Thus, these compounds act as amino acids in liquid ammonia as described below. Sulfamic acid behaves as a dibasic acid in liquid ammonia, whereas in water it acts as a monobasic acid. This is because NH2 group is not acidic enough to donate to water. Reactions of amino bases. The most common reaction in liquid ammonia involving amino bases are reactions of the amide ion, NH2 negative. Most commonly used amino bases in liquid ammonia is potassium amide, KNH2, because of its high solubility in liquid ammonia. The solubility of lithium amide and sodium amide is very small in liquid ammonia. Reactions of such solutions with metal ions in liquid ammonia are used for the preparation of metal amide, metal imide, and metal nitrides. AgNO3 plus KNH2 in presence of liquid ammonia is equal to KNO3 plus AgNH2 PPT. PbI2 plus KNH2 in presence of liquid ammonia is equal to Ki plus Pbi plus PbNH. TiNO3 plus KNH2 in presence of liquid ammonia is equal to KNO3 plus 2HNO3 plus tin. BiL3 plus KNH2 in presence of liquid ammonia is equal to Ki plus 2Hi plus BiN. Care should be taken in handling the imide and nitrides of the lead, thallium, bismuth respectively, and these detonate with explosion. Salts of these amino acids can be readily prepared by their reaction with very strong base in liquid ammonia. For example, sodium uride can be prepared by combining urea with sodium amide in liquid ammonia. It is important to note that sodium uride cannot be prepared in water. Similarly, aluminum salts combine with potassium amide in liquid ammonia to form soluble amide complex as shown below. AlCl3 plus 3KNH2 in presence of liquid ammonia is equal to AlNH2 plus 3KCl. Redox reactions. Oxidation reduction reactions are well known in liquid ammonia wherein the nitrogen and hydrogen of ammonia undergoes a change in the oxidation state. Redox reactions are classified in the three classes which are discussed below. First, redox reactions where alkali and alkaline earth act as reducing agent in ammonia. Alkali and alkaline earth metals dissolved in liquid ammonia are strong reducing agents. These blue-colored metal ammonia solutions undergo a variety of reactions in which the alkali metal gets oxidized while the other reactant gets reduced. 2Na plus NH4Br in presence of liquid ammonia is equal to 2NaBr plus NH3 plus H2. Na plus Cui in presence of liquid ammonia is equal to Cu plus Nai. K plus O2 in presence of liquid ammonia is equal to K2O2. K plus O2 in liquid ammonia is equal to KO2. 2Na plus S in liquid ammonia is equal to Na2Se. 2K plus NH3 plus N2O in liquid ammonia is equal to KNH2 plus KOH plus N2. Second, redox reactions where liquid ammonia acts as reducing agent. A number of reactions are known where liquid ammonia itself acts as a reducing agent. For example, catalytic oxidation of ammonia in the presence of platinum. 4NH3 plus 5O2 in presence of platinum is equal to 4NO plus 6H2O. Reduction of metal oxides. 2NH3 plus CO is equal to 3Cu plus N2 plus 3H2O. Oxidation of reactive metals. 2NH3 plus 3Mg is equal to Mg3N2 plus 3H2. Reduction of nonmetals. Cl2 plus 2NH3 is equal to NH4Cl plus NH2Cl. Third, redox reactions where liquid ammonia acts as a solvent. A number of redox reactions are known wherein liquid ammonia simply acts as a solvent. Oxidizing action of various oxidizing agents is weaker in liquid ammonia than in aqueous solution. Nitric acid is a very strong oxidizing agent in water, but does not act as an oxidizing agent in ammonia. Similarly, potassium permanganate is a strong oxidizing agent in water but behaves as a weak oxidizing agent in liquid ammonia. Potassium permanganate first reduces to potassium manganate and finally to manganese oxide by a solution of potassium in liquid ammonia. Solvolysis or ammonolysis. A solvotic reaction is defined as a reaction in which the solvent molecules react with the solute, splitting into two parts, one or both of which may become attached to the solute molecules. In most cases, the solvolytic process results in an increase in the concentration of either the anion or the cation, which is characteristic of the autoionization of the solvent. Nearly all the solvent inorganic halides, which, when dissolved in liquid ammonia, undergoes ammonolysis. A familiar example would be the ammonolysis of bone trichloride. BCl3 plus NH3 is equal to Cl3BNH3 in presence of liquid ammonia is equal to Cl2BNH2 plus NH4Cl. This reaction would continue until BNH2 thrice is formed. Similarly, the ammonolysis of titanium tetrachloride takes place in steps as follows. TiCl4 in liquid ammonia is equal to TiCl3NH2 in liquid ammonia is equal to TiCl2NH2 twice in presence of liquid ammonia is equal to TiClNH2 thrice in presence of liquid ammonia is equal to TiNH2 4. The important examples of ammonolysis are HgCl2 in liquid ammonia is equal to HgNH2Cl plus NH4Cl. SO2Cl2 in liquid ammonia is equal to SO2NH2 twice plus 2NH4Cl. Alkali metal hydrides and oxides are known to undergo ammonolysis reaction. MH plus NH3 is equal to MNH2 plus H2. M2O plus 2NH3 is equal to 2MNH2 plus H2O. Ammonolysis reaction with several organic substances have been studied in details. In ammonolysis, the atoms and ion from the compound undergoing ammonolysis is replaced by NH2 or double bond NH or triple bond N group. Thus, organic halides which undergo slow ammonolysis as the boiling point of liquid ammonia provides a mixture of primary, secondary and tertiary amines. C6H5Cl plus 2NH3, C6H5NH2 plus NH4Cl. Rx plus 2NH3 is equal to RNH2 plus NH4X. Rx plus RNH2 plus NH3 is equal to R2NH plus NH4X. Rx plus R2NH plus NH3 is equal to R3N plus NH4X, where R is equal to alkyl and X is equal to Cl, Br or I. Organic iodides have been found to undergo ammonolysis readily than the bromides and chlorides. Solvate ammoniates formation. When a solid is dissolved in a solvent and the excess of solvent is removed, the solid product obtained in most cases contains a number of molecules of the solvent attached to the solute by a chemical bond. Such a process is called solvation, and in the case solvent is ammonia, it is called ammoniation. The bonding that is involved in ammoniates may be explained in terms of coordinate, covalent, hydrogen bonding and ion dipole interaction. Some of the common examples are SO3 plus 2NH3 is equal to SO3 2NH2, BF3 plus NH3 is equal to BF3.NH3, CuSO4 plus NH3 is equal to CuSO4.4NH3, SiF4 plus NH3 is equal to SiF4.2NH3. Complex formation reactions. A number of complex formation reactions in liquid ammonia have been investigated which are similar to the complex formation reactions occur in water. For example, zinc is precipitated as zinc amide in liquid ammonia, which get dissolved in excess of amide to form soluble aminozincates complex. ZnNO3 twice plus 2KNH2 in liquid ammonia is equal to ZnNH2 twice plus 2KNH-NO3. ZnNH2 thrice plus 2KNH2 in ammonia is equal to K2ZnNH2 soluble amide zincate. Precipitation reaction. The formation of the precipitate when solutions of two compounds are mixed is one of the most common and familiar chemical reaction. These reactions are independent upon the solubilities of the products in a particular solvent. As a result, precipitation reactions are highly dependent upon the solvent employed. On mixing solution of barium chloride and silver nitrate in water, there is immediate precipitation of silver chloride. The reaction proceeds in the forward reaction because silver chloride is practically insoluble in water. However, the liquid ammonia in the direction of the reaction is reversed. It means that on mixing solutions of silver chloride and barium nitrate in liquid ammonia, it is barium chloride that is precipitated. The reaction proceeds in the forward reaction because barium chloride is practically insoluble in liquid ammonia. Similarly, metal bromides and iodides are precipitated when metal nitrates or ammonium halides are mixed together in liquid ammonia. NH4I plus ZnNO3 twice in liquid ammonia is equal to ZnI2 plus NH4NO3. Ammonium sulfide in liquid ammonia is used in precipitating many metal sulfides from metal nitrates solutions. NH4 twice S plus 2 AgNO3 in liquid ammonia is equal to Ag2S plus 2 NH4NO3. Barium methoxide in liquid ammonia can be precipitated out by combining potassium ethoxide with barium nitrate as given below. 2C2H5OK plus BaNO3 twice in liquid ammonia is equal to BaOC2H5 twice plus 2KNO3. Similarly, sodium carbamate can be precipitated in liquid ammonia by combining ammonium carbamate with sodium nitrate in liquid ammonia. NH2COONH4 plus NaNO3 in liquid ammonia is equal to NH2COONA plus NH4NO3. Many insoluble halides can be precipitated as complex amines in liquid ammonia as 2NaCl plus CaNO3 twice plus 8NH3 in liquid ammonia is equal to CaNH3 8Cl2 plus 2NaNO3. Advantages of liquid ammonia as a solvent. Following are the advantages of using liquid ammonia as a solvent. First, alkali metals dissolve cleanly in liquid ammonia without any chemical reaction. Second, alkali metal solutions in liquid ammonia are stronger reducing agent than hydrogen. Third, the tendency of liquid ammonia to undergo solvolysis reactions is smaller in comparison to water. Fourth, the solubility of ammonium salts in liquid ammonia finds extensive use in precipitating metal halides, sulfides, and sulfates. Disadvantages of liquid ammonia as a solvent. Liquid ammonia as a solvent has the following disadvantages. First, ammonia has a lower boiling point -33.35 degrees Celsius and consequently has a smaller liquid range, only 44.4 degrees Celsius at atmospheric pressure. The reactions in liquid ammonia can therefore be carried out only at low temperatures and high pressures. Second, specially designed apparatus and equipment is needed to carry out reactions in liquid ammonia. Third, liquid ammonia is hygroscopic and therefore at most precautions are needed to exclude moisture from the reaction vessel. Fourth, it has unpleasant smell. 8.5. Sulfuric acid as a non-aqueous solvent. Sulfuric acid is the most extensively studied of all the strongly acidic solvents. It is a good solvent for a variety of organic compounds. Most of the organic compounds accept protons in sulfuric acid and act as bases in it. Before we discuss the chemistry of sulfuric acid, it is appropriate to learn some of the physical constants of sulfuric acid which are listed below. Pure sulfuric acid 100% has a freezing point of 10.371 degrees Celsius. It can be prepared by adding aqueous sulfuric acid to fuming sulfuric acid, anhydrous sulfuric acid containing excess sulfur trioxide until a freezing point of 10.371 degrees Celsius is obtained. Fuming sulfuric acid is also called oleum H2S2O7. The freezing point diagram for H2O SO3 system in the neighborhood of 100% H2SO4 is shown. A careful inspection of the table 8.6 reveals that sulfuric acid is a highly viscous solvent, suggesting that the highly associated nature of the solvent through hydrogen bonding. As a result, the strong hydrogen bonding high boiling point is also justified. The high specific conductance of 100% sulfuric acid indicates that the solvent autoionizes to a considerable extent. We have already learnt in the autoionization of water and ammonia according to the following equations. 2H2O is equal to H3O positive plus OH negative. 2NH3 is equal to NH4 positive plus NH2 negative. The autoionization of sulfuric acid can be expressed as 2H2SO4 is equal to H3SO4 positive plus HSO4 negative. The ionic product constant of sulfuric acid is given by K is equal to H3SO4 positive, HSO4 negative is equal to 2.4 into 10 raised to power minus 4 at 25 degrees Celsius. In addition to the autoionization or autoprotolysis, there are other important dissociation equilibria in case of 100% sulfuric acid. Among the most important of these is the self-dissociation reaction 2H2SO4 is equal to H2O plus H2S2O7. Since water behaves as base in sulfuric acid, the disulfuric acid H2S2O7 acts as an acid in sulfuric acid. We must consider two more equilibria according as H2O plus H2SO4 is equal to H3O positive plus HSO4 negative. H2SO4 plus H2S2O7 is equal to H3SO4 positive plus HS2O7 negative. The first of the equilibria proceeds extensively to the right, whereas the second proceeds to the right to a small extent. From the four equilibria mentioned above, an additional equilibria can be derived. 2H2SO4 is equal to H3O positive plus HS2O7 negative. This derived equilibrium is called the ionic self-dehydration reaction. The values of the equilibrium constants of the above equilibria are given in table 8.8. The total molar concentrations of species other than H2SO4, that is HSO4 negative, H3SO4 positive, H3O positive, HS2O7 negative, H2S2O7 and water is 0.424 molar at 25 degrees Celsius. Acid-base reactions in sulfuric acid. The autoionization of sulfuric acid results in the formation of hydrogen sulfate ion HSO4 negative and sulfuric acidium ion H3SO4 positive. 2H2SO4 is equal to H3SO4 positive plus HSO4 negative. Accordingly, the strongest base can exist in 100% sulfuric acid in the hydrogen sulfate ions HSO4 negative. Thus, strong bases in the system are solutes, which yield high concentration of the ions in sulfuric acid solution. Alkali and some other metal hydride sulfates are strong bases, similar to metal hydroxides in the aqueous system. Acids. Sulfuric acid is a very strong acid, and almost all chemical species which react with it forms the hydrogen sulfate ion. Thus, a majority of substances behaves as bases in it because of the strong tendency of H2SO4 molecule to donate protons. Molecules exhibiting basic tendencies are all leveled to a strength of HSO4 negative ion. As already discussed, majority of the substances that behave as acid in the aqueous solution do not show acidic properties in sulfuric acid. Rather, these behave as bases. For example, acetic acid, phosphoric acid, nitric acid, hydrogen fluoride, etc. all behaves as basic in sulfuric acid. Even perchloric acid, which is one of the strongest known mineral acid, is the only slightest ionized in sulfuric acid and behaves as a weak acid. HClO4 plus H2SO4 is equal to H3SO4 positive plus ClO4 negative. Only one of the few substances that behaves as an acid in sulfuric acid is disulfuric acid. It is formed from sulfur trioxide and sulfuric acid. SO3 plus H2SO4 is equal to H2S2O7. H2S2O7 plus H2SO4 is equal to H3SO4 positive, HS2O7 negative. The only strong acid in sulfuric acid is tetrakis, hydrogen sulfate, borate, HbHSO44. The compound has not been prepared and isolated in the pure form, but solutions of this acid can be prepared in sulfuric acid as H3PO3 plus 6H2SO4 is equal to BHSO4 negative plus 3H3O positive plus 2HSO4 negative. Addition of sulfur trioxide to the above solution removes the H3O positive and HSO4 negative ions as BHSO4 negative plus 3H3O positive plus 2HSO4 negative plus 3SO3 is equal to H3SO4 positive plus BHSO4 negative plus 4H2SO4. Both tin and lead tetraacetate dissolved in sulfuric acid to give strong acids. SNOAC4 plus 8H2SO4 is equal to SNH2SO4 6 whole to negative plus 4CH3COH2 positive plus HSO4 negative. Thus, there is a small number of substances which behave as acidic in sulfuric acid. They are given in the table with their ionization constants. For example, KHSO4 is equal to K positive plus HSO4 negative. Since the anions of normal salts of the most of the inorganic acids are actually strong bases, then is the hydrogen sulfate ion. Such salts undergo complete solvolysis in sulfuric acid to yield hydrogen sulfate solutions. For example, NaCl plus H2SO4 is equal to Na positive plus HSO4 negative plus HCl. Na3PO4 plus 3H2SO4 is equal to 3Na positive plus 3HSO4 negative plus H3PO4. NaNO3 plus H2SO4 is equal to Na positive plus HSO4 negative plus HNO3. A large number of covalent compounds, both organic and inorganic, undergo proteolysis in 100% sulfuric acid, giving hydrogen sulfate ion. For example, nitric acid, which is strong acid, and acetic acid, which is a weak acid, in aqueous solution both behaves as bases in sulfuric acid. HNO3 plus H2SO4 is equal to NO2 positive plus H2O positive plus 2HSO4 negative. Similarly, phosphoric acid behaves as a base in sulfuric acid. H3PO4 plus H2SO4 is equal to PO4OH4 positive plus HSO4 negative. Other compounds that behaves as basic in sulfuric acid are amides, esters, ketones, phosphines, urea, formic acid, and oxalic acid. Unlike acetic acid, formic acid and oxalic acids are stable in sulfuric acid and decompose to give carbon monoxide. HCOOH plus H2SO4 is equal to CO plus H3O positive plus HSO4 negative. A number of examples are known where the organic compounds first undergo proteolysis followed by complex reactions. For example, C2H5OH plus H2SO4 is equal to C2H5O SO3H plus H3O positive plus HSO4 negative. It is found that all the species that are basic in water are also basic in sulfuric acid. For example, OH negative plus 2H2SO4 is equal to H3O positive plus 2HSO4 negative. NH3 plus H2SO4 is equal to NH4 positive plus HSO4 negative. Ethers. Ethers are monoprotonated in sulfuric acid, and the reaction is further followed by solvolysis. Solubilities in sulfuric acid. The dielectric constant of sulfuric acid 110 is greater than that of water 90. As a result, sulfuric acid should be a better solvent for ionic solutes. However, because of its high degree of hydrogen bonding in sulfuric acid, it is difficult for a solute to dissolve unless the molecular aggregation present in sulfuric acid is disrupted. In such cases, the solute is highly solvated. Table 8.10 gives the solubilities of various inorganic compounds and the resulting solvates formed. Solvation occurs only when the solution is ionic or reacts with a solvent to form ions. Solvation also occurs in cases where the solute itself is strongly hydrogen bonded to sulfuric acid molecules. A solute behaves as a non-electrolytic in 100% H2SO4 if it is very weakly basic in nature and does not accept protons from sulfuric acid. However, for such a solute to dissolve, it must be capable of forming hydrogen bonds with sulfuric acid. Alkali and alkaline earth metals halides reacts immediately with 100% sulfuric acid with the evolution of hydrogen chloride in case of metal chlorides and bromine in case of metal bromides. It is important to note that because of the highly acidic nature of sulfuric acid coupled with its ability to bring about solvolysis, many of the solution process involve the formation of several different ions or molecules from a single solute molecule. Some of the examples are illustrated below with the number mu or ionic or molecular species formed from one solute molecule. NO2OH plus 2H2SO4 is equal to NO2 positive plus H3O positive plus 2HSO4 negative, mu is equal to 4. N2O4 plus 3H2SO4 is equal to NO positive plus NO2 positive plus H3O positive plus 3H2SO4 negative, mu is equal to 6. The values of mu are determined cryoscopically. Conductance in sulfuric acid. Sulfuric acid is highly viscous and the viscosity of sulfuric acid is 25 times that of water. As a result, the mobility of various cations and anions in 100% sulfuric acid should be quite low as compared to that of water. Let us consider the relative mobilities of Na positive, K positive, Ba2 positive plus H3O positive in sulfuric acid as well as in water. The ionic mobilities of Na positive, K positive, Ba2 positive plus 3H3O positive in 100% sulfuric acid is very small. It is in line with the viscous nature of H2SO4. However, a careful inspection of the table 8.11 reveals that the mobilities of H3SO4 positive plus HSO4 negative are very much higher than those of other ions in 100% H2SO4. In spite of the highly viscous nature of 100% H2SO4, it has an Appreciable electrical conductance. Because of the high mobilities of H3SO4 positive and HSO4 negative ions together with the considerable degree of ionic dissociation of sulfuric acid, the exceptionally high mobility of HSO4 negative can be easily explained on the basis of very low transport number of the cation in solutions of various metal hydrogen sulfates in 100% sulfuric acid. If you recall, transport number measures the relative amount of current carried by the cation and anion of the given electrolyte. A high T negative value indicates that the anion moves much faster than the cation, hence conducts a large fraction of the total current compared to the countercation. Table 8.12 lists the transport number of various metal hydrogen sulfates in sulfuric acid solutions. An inspection of table 8.11 reveals that H3SO4 positive and HSO4 negative ions have mobilities that are greater than any other ions in sulfuric acid. It is also interesting to see that the ions H3O positive and OH negative in aqueous solution have exceptionally high mobilities. The mobilities of H3SO4 positive and HSO4 negative ions are unaffected by the high viscosity of 100% H2SO4. This is because of the ions H3SO4 positive and HSO4 negative conducted by the proton transfer mechanism, which is also true for the high mobilities of H3O positive and OH negative ions. In aqueous medium, we can picture water molecules connected by hydrogen bonds in a network. The effective movement of the H3O positive ions through the aqueous solution can be imagined by the very minor shift of proton along the chain in the manner indicated by the arrow. There is in fact no mass movement of water molecule involved in this process. It is only the shift of protons that occur very fast. A similar mechanism can be proposed to account for the mobility of OH negative ions in water. Similar to water, the molecules in 100% sulfuric acid are connected through hydrogen bonding in a network. The effective movement of H3SO4 positive and HSO4 negative ions occur through the proton transfer mechanism, as in the case of water explained above. The mechanism is illustrated below for H3SO4 positive and HSO4 negative ions. Successive transfer of protons along hydrogen bonds result in the effective movement of H3SO4 positive ions through the solution without the need of actual movement of individual ions. It is because of high mobilities of H3SO4 positive and HSO4 negative, the electrical conductances of various acids and bases in a 100% sulfuric acid are determined by the number of H3SO4 positive and HSO4 negative ions per mole of a particular acid or base in sulfuric acid solution. In other words, the measurement of electrical conductance provide valuable information concerning the ionization process of certain electrolytes. In brief, 100% sulfuric acid is a highly acidic medium with high dielectric constant. It has high electrical conductance. It is nearly 25 times more viscous than water. Very few substances dissolve in 100% H2SO4 as non-electrolyte. Most of the substances, especially the organic compounds, behave as bases in sulfuric acid. Many ionic compounds are soluble in sulfuric acid but undergo solubilisis during the solution process. The strongest base available in sulfuric acid is the HSO4 negative ion, and the strongest acid is H3SO4 positive. The neutralization acid in sulfuric acid system involves the interaction of H3SO4 positive ion and H3SO4 negative ion. H3SO4 negative plus HSO4 negative is equal to 2H2SO4. 8.6. Liquid sulfur dioxide as a non-aqueous solvent. Liquid sulfur dioxide is a gas at room temperature and atmospheric pressure. It can be easily liquefied and can be maintained in the liquid phase in ordinary Dewar flask. It is used to carry out the number of chemical reactions. It is a non-protic solvent. Some of the important physical properties of liquid sulfur dioxide are listed below. A close inspection of the table 8.13 reveals that the dielectric constant of the liquid sulfur is low, which makes it an ideal solvent for covalent compounds than for ionic substances. Bromine, chlorine, iodine, monochloride, thionyl chloride, carbon sulfide, phosphorus trichloride, phosphorus oxychloride are miscible in SO2 in all proportions. With few exceptions, liquid sulfur dioxide is an excellent solvent for a variety of organic solvents. Amines, ethers, alcohols, esters, sulfides, carboxylic acids, and mercaptans are readily soluble. Alkanes have only limited solubility in sulfur dioxide, whereas alkenes and aromatic hydrocarbons have higher solubilities in the liquid sulfur dioxide. It is the different solubilities of alkanes and alkenes in liquid sulfur dioxide that is the basis of refining of petroleum. Among ionic compounds, the iodides and thiocyanates are in general most soluble in liquid sulfur dioxide. The solubilities of alkali metal halides in sulfur dioxide decreases in the order I negative more than Br negative more than Cl negative. A similar trend is also observed in liquid ammonia. It is important to note that the tetramethylammonium halides, where X is equal to Cl, Br, and I are freely soluble in liquid sulfur dioxide. The extreme solubility of these compounds is because of the lower lattice energies of these compounds. Autoionization. The electrical conductivity of pure liquid sulfur dioxide can be explained in terms of self-ionization according to the following equilibrium. 2SO2 is equal to SO2 positive plus SO3 2 negative. The thionyl ion is analogous to the hydronium and ammonium ion, whereas the sulfite ion is analogous to the hydroxide ion and amide ion in water and ammonia solvent system respectively. Reactions in liquid sulfur dioxide. Reactions occurring in liquid sulfur dioxide can be broadly classified as acid-base reactions, solvolytic reactions, solvation reaction, precipitation reaction, complex formation reaction, redox reaction, reactions with organic compounds, amphoteric behavior. Let us discuss these reactions in detail one by one. Acid-base reactions. Acid-base reactions, which are also called neutralization reactions, can be better described as mathematical reactions. Liquid sulfur dioxide has been shown to autoionize as, according to solvent system concept, a substance capable of giving the cationic characteristic of the autoionization of the solvent in an acid, whereas a substance capable of giving an anionic characteristic of the autoionization of the solvent is a base of the system. Thus, compounds like thionyl chloride, thionyl acetate are acids of the sulfur dioxide system. Accordingly, all compounds with anionic sulfite are the basis of the system. For example, potassium sulfite and cesium sulfite are the basis of sulfur dioxide system. Some of the acid-base or neutralization reaction in liquid sulfur dioxide system are: A. Reaction between thionyl chloride and cesium sulfate. SOCl2 plus CsSO3 in liquid sulfur dioxide is equal to 2CsCl plus 2SO2. Second, reaction between thionyl bromide and tetramethyl ammonium sulfide. SOBr2 plus Me4N twice SO3 in liquid sulfur dioxide is equal to 2Me4NBr plus 2SO2. Third, reaction between thionyl thiocyanate and potassium sulfite. SOSCN twice plus K2SO3 in liquid sulfur dioxide is equal to 2KSCN plus 2SO2. Solvolytic reactions. Solvolytic reactions in liquid sulfur dioxide are much less common than in water. Some of the solvolytic reactions include reaction of diethyl zinc with sulfur dioxide at dry ice temperature. Solvolysis of ammonium acetate, solvolysis of binary halides. There are a number of binary halides such as SbCl3, SbCl5, SiCl4, SnCl4, VCl5 and MoCl6 which do not undergo solvolysis reactions in liquid sulfur dioxide. Solvolysis of alkali metal halides. 8 Kbr plus 8 SO2 is equal to 4 K2SO3 plus 4 SOBr2. Solvation reaction. A reaction in which one or more molecules of the solvent is attached to the solute is called the solvation reaction. A number of such reactions are known in liquid sulfur dioxide. It is found that more soluble compounds form solvates in sulfur dioxide. Typical examples of solvates in the sulfur dioxide system are given. Precipitation reactions. Precipitation reactions are conveniently carried out in liquid sulfur dioxide. Precipitation reactions are dependent upon the solubilities of the possible products in a particular solvent. Thus, a number of compounds can be precipitated in liquid sulfur dioxide by carrying out reactions with soluble compounds in sulfur dioxide. Some of the typical examples are cited below. 2CH3COAG plus SOCl2 in sulfur dioxide is equal to 2AgCl plus SOCH3COO twice. 2 Kbr plus SOCl2 in liquid sulfur dioxide is equal to 2 KCl plus SOBr2. Solvolytic reactions. Solvolytic reactions in liquid sulfur dioxide are much more less common than in water. Some of the solvolytic reactions include reactions 2Ki plus SOCl2 in liquid sulfur dioxide is equal to 2KCl plus SOI2. Thionyl iodide. Thionyl acetate has not been isolated. It decomposes into acetic anhydride and sulfur dioxide. Thiocyanate is, however, stable in dilution solution and has been isolated. Some of the other precipitation reactions in sulfur dioxide are SbCl3 plus LiI in presence of liquid sulfur dioxide, SbI3 plus 3LiCl. Complex formation reactions. A number of reactions that involve complex formation are known in sulfur dioxide. Iodine is soluble in liquid water. Sulfur dioxide, but its solubility increases tremendously on addition of potassium and rubidium iodide. The tremendous increase in the solubility is due to the formation of complex Ki3 or RbI3. Ki plus I2 is equal to Ki3. Similarly, the solubilities of cadmium iodide and mercuric iodide are increased by the addition of potassium and rubidium iodide in the solvent owing to the formation of complex ion. Hgi2 plus 2Ki in liquid sulfur dioxide is equal to K2HgI4. A number of examples of complex ion like SbCl negative, hexachloro, antimonate involving antimony compounds are given below. Redox reactions. Liquid sulfur dioxide does not act as oxidizing agent or reducing agent of its own. It acts as a medium in which redox reaction may occur. For example, sulfur dioxide cannot reduce iodine. However, addition of tetramethyl sulfite reduces iodine to iodide ion and in turn gets oxidized to sulfate. A solution of ferric chloride will quantitatively oxidize potassium iodide to free iodine. Some other oxidation reduction reactions occurring in liquid sulfur dioxide are given below. Nitrosyl compounds in above example act as an oxidizing agent in liquid sulfur dioxide. Reactions with organic compounds. Liquid sulfur dioxide is a useful medium for carrying out several types of organic synthetic reactions. This is mainly because of its inertness and non-inflammability. Some of important reactions are sulfonation of aromatic hydrocarbons either by sulfur trioxide or by chlorosulfuric acid. Friedel-Crafts type reactions. Addition and substitution reactions of bromine. Amphoteric behavior. A number of reactions carried out in liquid sulfur dioxide show striking resemblance to the behavior of amphoteric hydroxides in aqueous systems. For example, treatment of aluminium chloride in sulfur dioxide with tetramethyl ammonium sulfite results in the formation of gelatinous precipitates of aluminium sulfite. If the gelatinous precipitate of aluminium sulfide is rapidly treated with excess of tetramethyl ammonium sulfite, the precipitate redissolves just as aluminium hydroxide dissolves in the excess of sodium hydroxide solution. Now, if the acid thionyl chloride is added to the resulting solution of liquid sulfur dioxide, aluminium sulfite reprecipitates. Sulfur dioxide has been shown above to be a very useful solvent for a variety of reactions. Its use, especially in refining of petroleum products, is very important. However, it is very toxic and has very unpleasant odor. Utmost care must be exercised in its use in view of its harmful physiological effects. Breathing large quantities of sulfur dioxide has been found to be fatal. Thank you.